Yeah, welcome to the Ceramic Labs. This is Sonny Lightfoot, who's
research associate and research technician.
And I'm Tavs Jorgensen. I'm associate professor here at CFPR. In the Ceramic Lab, we do a range of ceramic-based projects, but we also looking really to use the knowledge and the findings that we have through the projects that might be ceramic based in a lot of other contexts and a lot of other materials. So we're really looking to use the knowledge as broad as possible and we're really curious in terms of materials and applications and technology. So a very kind of fluid approach, even though that it is kind of labeled the Ceramic Labs. But to be, just to give you a quick overview of some of the projects that are going on in here, we've got a powder 3D printer, ceramics powder 3D printer here. It's a long-standing research interest for CFPR. CFPR has been leading in that particular area of research and development for a number of years, and with the new funding, we've been able to buy the kind of next generation of machines for 3D printing in powder, and kind of continue and develop our research even further in that area. We have paste 3D printing here, which is just like the powder 3D printing. The principle is the same, where you build up objects by layers. So in the powder, it will layer the powder up and it will bind the layers of powder with a binder. With the paste 3D printing, essentially it's a paste that kind of being squeezed out into layers and thereby building up objects. But it's a particular area that Sonny will be kind of going into more details on in a few minutes. We have other sort of smaller projects in the ceramic area. We've got a water filter project, developing ways of filtering water in developing countries. It's a very efficient way of removing waterborne diseases from drinking water. We also do some work on biocomposites, 3D printing with organic materials, biomaterials, and this is also an area that Sonny is kind of leading on. But yeah, it's certainly an area that we are developing a strong interest in and really looking to utilize knowledge developed for ceramics, ceramic paste or plastic ceramic, and to kind of transfer that knowledge into other materials and compounds. But one of the key projects for us, for me, for Sonny and I, is ceramic extrusion, profile extrusion. So it's different from 3D printing with ceramic. It's where you have a profile, a static profile, and you are forcing clay through a profile or a die, and you create artifacts or products in that way. It's a process that's used a lot in industry for architectural components, so bricks, roof tiles, lots of other kind of paneling and ceramic parts, pipes are done through extrusion. It's an incredibly efficient way of producing and heavily utilized. But it's also an area that is underexplored in terms of innovation. They've been using many of the same processes and some of the same profiles for years, if not for decades. And we, with this project, really wanted to look at ways that digital fabrication could be used to explore new ways to use extrusion, particularly in terms of developing of the profiles. They're called the dies, and we have explored using 3D printing, plastic 3D printing, rather than than metal, which is traditionally used for the dies, to create the dies very simply from 3D printed parts. It is one of the areas that has kind of held back innovation in the ceramic industry, that the tool making for the dies and that whole kind of workflow has really been hampered by cost and by the time it takes to develop new tools and new workflows. So that's really what we'll be looking at. So it seemed to work. That we can use three cheap consumer plastic 3D printers to produce the dies, and they hold up to the pressure really quite well. And this, in that way, it's been relatively straightforward and successful to prove that you can 3D print the dies very quickly. But it is a project that's kind of looked at tool making in the whole sector much more broadly. So when we started on the project, we wanted to buy an extruder that we can actually do the research on. We could develop the use of 3D printed dies on, and we simply couldn't buy one. We tried to get one from America, but it was incompatible with the UK kind of power or electric specifications, and so it really seemed like there was a complete gap, both for industry and also for us, in terms of machinery where we could innovate on and we can test on. So we had to build our own extruder, and so the tool making kind of was a big part of actually making the extruder in the first place. And also in that process we used digital fabrication. We used, in the case of extruder, we used laser cutting of metal. We used a local company to produce particular specialist parts or brackets that we needed to create the extruder, but also used off-the-shelf parts to construct the machine. So whatever we could get in terms of standard components we used, and then anything specialized we then got produced via digital fabrication and laser cutting in particular. We'll give you a quick demo on the extruder.
Yeah, sure. So this, like Tavs said, this is the extruder that we've made ourselves, and essentially it's a hydraulic pump which pumps the oil to our ram or our cylinder, which works like a piston. So using this lever, we can push the ram forward or move it back, and when we're moving it forward, essentially we've preloaded this barrel with clay, and the ram's pushing forward, pushing that clay, and then squeezing it through our 3D printed die. So having made it and it being a hydraulic system, there's some advantages of it being able to produce really high pressures, so we can test different hardnesses of clay, and the machine can hold up to that really well. And also we've been able to put features in like the pressure bypass valve, which allows us to control the pressure that we're extruding at. So that means we could extrude much firmer clays by increasing the pressure, and we can also control the speed of our extrusion while we're extruding. So we can turn the pressure up to increase the speed and turn the pressure down to decrease the speed. So I'll just show you that now. See it running fast there, then we can slow it right down. So that is the extruder.
Other parts of the research have involved ways of kind of dealing with the complex rheology that is involved with extrusion. So when you extrude things or profiles that are asymmetrical, like this is a design for a louver, a window louver for solar control, a ceramic window louver. When you have dies that are asymmetrical, you would typically find that the clay would be moving quicker in certain areas of the die than others, and you typically get issues like this where the extrusion would curve and ripple. And we've been able to find ways in industry they typically deal with that by really heavy engineering of big kind of metal parts that will move inside the extruder to block the flow of the clay as it moves into towards the nozzle. But we've been working other ways of addressing that by printing other nozzles and kind of dealing with that issue through digital fabrication and in a much more kind of quick iteration to address that issue of the flow of the clay. Other aspects that we were looking at is to further in terms of the kind of tool making aspects where we've developed scripts and software tools that can generate the complex dies like this, where you have a multiple core and really quite a complex geometry. These dies have been generated automatically from a script that we developed, where you can just insert a particular pattern or a particular tiling pattern, and then it generates the rest of the geometry of the dies automatically from the tile pattern. We've developed dies that can coat the extrusions as they emerge from the extruder, both on the inside and the outside. We've been exploring ways of bending the extrusions as they emerge from the extruder through the use of robots. So a whole range of kind of different approaches using and exploring the use of digital technology, how that can help innovation and new approaches with the ceramic extrusion process, which is an area that has got great potential in terms of production, but is currently really underutilized. I think we'll move over to the 3D printing with ceramic paste, which Sonny's going to outline our research on.
Yeah, so this system essentially uses the extruder as well, but rather than using pushing the clay through a die, the ram is pushing the clay up through this pipe, which is being delivered to our print head here, and our print head then has an auger, a screw, that spins and pushes, gives a lot more precision to then extrude the clay out as a bead. And the advantage of having an auger means that we can also spin the auger in reverse, and it'll retract the clay, so stop it flowing out. And again, this project is centered around tool making, again, because this sort of scale of paste extruder is not easily or readily available. So we've had to develop our own using, in this case, the first prototype is just standard plumbing fittings, brass fittings, and the screw inside is just a standard wood screw, a bore screw, with the idea that from that prototype we can develop out more precise tooling, so develop our own augers using other digital fabrication as well as 3D printing, CNC milling to be able to produce these in stainless steel and brass, and be able to 3D print the housing of the print head as well. So the idea is to print large scale pieces with this, potentially for architectural use, for panelling and that sort of thing. And one of the issues or problems that needs to be addressed, or that we're addressing with this paste extrusion, is an uneven bead of clay being extruded. So when we're pushing the clay through the extrusion barrel, due to the high pressure, there's a thing that happens called dewatering, where water is essentially pushed out of the clay due to the pressure. So it changes the consistency of the clay throughout the extrusion. So you could start off with very soft clay, and you could end up with much firmer clay by the end. And because of that, the pressure needs to be adjusted to keep a consistent bead. So this is what this piece of the setup is. This prototype is essentially sensors which are detecting the thickness of the bead, and we've told it what size we want that to be. And if it detects that it's below the correct thickness, it will then use this step motor, which would normally be attached to the pressure bypass valve, so it could turn and increase the pressure if the bead is too thin, and likewise if the bead is too wide, it can decrease the pressure. So it's a feedback loop to be able to change the pressure on the extruder to produce a consistent bead. So these are just examples of stuff that's already been extruded, so that we could show here on the graph a live feed of the sensor. So you can see here, while it's up in the air, not sensing, it's flat, and then these peaks are the two different beads that it's measuring. And here is the live video of it printing one of these beads that we've already created.